which of the following is correct order for the Sn2 reactivity, the decreasing order of the Sn2 reactivity. Here in the Sn2 mechanism, the nucleophile attacks on the carbon which is attached to the halogen, right? So the carbon, being more electronegative atom, is dealt negative and the carbon will be dealt a positive, and in the Sn2 the nucleophile attacks on the back side of this carbon at 180-degree angle to the leaving group. Here the chlorine is a leaving group, and this hydroxide approaches very close to the carbon and it forms the transition state here. In this transition state, this particular carbon is attached with the chlorine and the hydroxide, but the bond breaking starts basically between the carbon and the chlorine, and bond formation starts between carbon and the hydroxide. So this is a transition state in which the nucleophile attacks from the back side of the carbon. And here the very important requirement for the Sn2 mechanism is that the groups attached with this particular carbon, right? And these groups, they should be small. Okay, if the size of these groups is very big, right, like we have a tertiary alkyl halide, if there are 3 alkyl groups, then this nucleophile cannot approach it, right? It will be very difficult for the nucleophile to approach and form a transition state in that case, right? The smaller the size of these groups, the better it is for the Sn2 mechanism, right? And after the transition state, you will see that this chlorine finally comes off as the Cl negative and the hydroxide forms the bond, and these 3 hydrogen atoms here, they flip to the other side. Okay, so that means here in the Sn2 mechanism there is a complete inversion of configuration as well. And the reactivity order, as I discussed, that the requirement is that these groups should be smaller. Okay, that means the primary alkyl halide will be more reactive than secondary than the tertiary. Alright, so the primary alkyl halide is more reactive than secondary than tertiary, which means that this is the order. This is the primary alkyl halide. Here you have a carbon attached with the halogen and 2 hydrogens and only 1 alkyl group. Here you got the 2 alkyl groups, right? So this is the secondary one and this is the tertiary one, and this will be the least reactive, and the nucleophile always finds it very difficult to approach because of the steric hindrance between these 3 alkyl groups and the nucleophile. So this won't be able to approach and form a transition state. So the option B here. Tertiary alkyl halides are practically inert to the Sn2 substitution mechanism. Just we discussed that because of the bulky size, right, of the groups attached to the carbon here, nucleophile will find it very difficult to approach to the carbon, right? So because of the steric hindrance, right, because of the steric hindrance between the alkyl groups and the nucleophile, Sn2 is practically inert, right? That means for the tertiary alkyl halides, they don't follow the Sn2 mechanism. Now for the Sn1 reaction, we know it is the carbocation that is formed as an intermediate. We have to compare the different pairs of alkyl halides here. In every Sn1 mechanism, the first step is the loss of a halogen, and then what do you get? You get a carbocation. And the reactivity of the alkyl halides in Sn1 basically depends on the stability of a carbocation. The more the stable this carbocation is formed there, the more the reactive alkyl halide will be. Alright, so if you look at here these two and you compare, what will be the carbocation in the Sn1? In case this carbon, this halogen is lost here and you get a carbocation, the carbocation will be like this, right? This is oxygen and the CH3. This is the carbocation, and now this oxygen with the electron pairs available with it, the lone pairs, it can undergo the resonance, right? So this electron pair can form a bond with it and it will undergo the resonance here, right? The resonating structure will be like this. For this carbocation, you get a resonating structure with this one. Okay, and from here the carbocation will be over here, right? So if you remove this chlorine here, you get a carbocation like this, oxygen CH3, and you got the positive charge here. This is the carbocation. Now the lone pair of electrons on the oxygen cannot stabilize this carbocation. There is no resonance possible, right? So resonance is not possible here in this case. Okay, while as here in this carbocation is resonance stabilized, so this is more stable. That means this alkyl halide will be more reactive than this one. Alright? Resonance stabilizes the carbocation. The more the stable carbocation, the more reactive the alkyl halide. Let's take another example. Here you see from this particular alkyl halide, if you remove the chlorine in the Sn1 mechanism, you get a carbocation there, and this lone pair of electron cannot delocalize it again. Alright, so that means the carbocation will be like this. Right? When there is the loss of halogen, you get a carbocation, and this carbocation cannot be delocalized by this pi electron pair because the carbocation is not at the allylic position, right? In this case here, when you remove this chlorine here as Cl negative, you get a carbocation over here, and that can be resonance stabilized. Alright, so you have a double bond here, a positive charge here. Now resonance is possible, right? You get a resonating structure like this. Okay, you get a double bond here, and the positive charge will be over here, and then again this will go back, and you get the first one back. So because of the resonance here, you can say the second one is more reactive, this one is more reactive than the first one. Here again we have two alkyl halides. In this case, when it follows the Sn1 mechanism, loss of a chlorine is there, and you get a carbocation there. Now you have a benzene ring attached to this one, and you have a carbocation at the allylic position. Again, it can undergo resonance, right? This carbocation can undergo the resonance here, so this positive charge will be delocalized over this ring. But in this case, you have a carbocation over here, and that carbocation is away from the ring. It's not in the conjugation, right? This is not a conjugate system here. The carbocation cannot be delocalized by this electron pair because it's not present at the allylic position, right? So no resonance is possible here, no resonance stabilization, whereas here the resonance is possible. So this carbocation is more stable. That means the first one here is more reactive than the second one. Hope you got it. Thanks for watching the video. Bye for now.